in good shape. We've got the area working fine. So all we want to do now is implement the gliding. And to implement the gliding, we just have to do the same thing that we did before, right? Where we update, basically using that same idea here, where we did our sort of our bounce equation, right? Where we actually take away all of the bounce velocity and just leave the remaining velocity, right? So if we want to do that, we still have the exact same code essentially, but I'm going to make it a little bit cleaner. So basically, if we go down here, I'm going to say that after we do this test wall bit, I'm going to go ahead and say that we got to update our velocity instead of doing it this way. And what we're going to do is we're going to do this inner product thing. You notice that the way that this is set up, it's saying that the existing velocity, we subtracted away the part that we didn't want anymore of that velocity, right? And by doing the way that we did that is we used an inner product with essentially the normal, if you remember, the normal to the wall that we hit. And what's nice about this equation is this actually works whether or not you hit a wall, because if we just set the normal of the wall to be 0, 0, this term would evaluate to 0, right? So what we could do is just say we always update the velocity with whatever wall he hit, and then we just have a wall normal right here that we're going to track. So we have wall normal, and it's going to be equal to 0, 0 always, right? And then we're just going to update that along with our t-min. Actually, trying to think of how I want to do this. Because I don't think this thing really knows what the wall normal is. So let's do it this way for now. Right? Wall normal equals whatever the normal would be. And so we're basically just doing the exact same code that we did before. Only this time I'm setting an arbitrary wall normal. So we could expand this code, I guess, to use walls that were not... Like, nothing in the code now really counts on the fact that the walls are horizontal or vertical, except our sort of not particularly good solution up here to testing the wall. It's this code right here would have to get a little bit better to handle a slanted wall, but that's about it. So what I want to do is say, all right, we can return whether we hit or not. So hit equals false, and in this case, hit equals true, right? So we'll return true, return hit. And now I'll just go ahead and set the normal to what I know each of these wall normals to be, and off we go. So in this case, I'm testing against the min corner x, so that normal would be in that direction. For the max corner x, it would be in the opposite direction x. Same thing here and here, right? And so I believe that should update our velocity correctly now. Excuse me. So we should be able to glide if I didn't mess it up, which I may have. And it looks like I did. Did I forget to... what did I forget to do here? So wall normal... I feel like... Why is he stopping there? What did I Totally trivial now. So let's go back to our diagram that we had before and see if with the dot product we can now solve the problem that was so sort of weird before and difficult. Happen. And so what I want to do is I want to say that there's going to be some kind of inbound vector here, right? There's going to be an inbound vector. And what we want to do is we want to take this inbound vector and we want to reflect it. Well, it's hard to draw today for some reason. I can't seem to draw good lines today. We want to reflect it out the other way, right? The sort of the notion of what's going to happen when you do a bounce is something coming in is going to get reflected almost as if this thing was a mirror, right? And so we want to think about the incoming vector as somehow giving us the information that we would need to compute whatever the outbound vector is, right? And so what exactly is happening here in terms of this impact and response, right? Well, there's some things that we probably aren't going to think about really. Like I said, we're not doing deformable dynamics, so like the fact that when something hits something else that makes a dent or things like that, we're not really going to think about at this point. But what we are going to think about is the fact that whatever is sort of the velocity that comes in here, in some sense that velocity has to be conserved, right? There's a certain amount of physics involved here where if we've got a certain amount of velocity coming in, we'd expect that amount of velocity to be the same leaving, right? Because of conservation of momentum and so on, all of your nice physics laws, minus however much energy goes into this impact. Right? So there's probably going to be some amount of energy lost in the fact that you do make a dent and so on. And so we may want to simulate that as well, that loss of energy that comes in here, in addition to what's going to happen otherwise. Even if we don't simulate modifying the wall, we may want to make the bounce more realistic by saying that it doesn't bounce off at full speed. It loses some of its energy in that impact, right? Now, what's happening when this thing hits this wall, right? Well, one of the interesting things about this is this case starts to talk about vectors in terms of their components, and it's kind of interesting to sort of see what's going on there. Well, what's going to happen is, if I look at, I know that this vector is composed of two pieces, right? Because we've talked about this quite a bit. It's composed of its y portion, and it's composed of its x portion, right? And if I think about what happens to this vector, well, the wall is only stopping one of those portions, right? It's only stopping the y portion, right? So if I wanted to reflect this guy, I really don't want to stop his x motion at all. His x motion can continue just as it was because there is no wall horizontally here to prevent him from going somewhere. It's only this wall here that's preventing him from moving vertically, right? And so I could think about taking this vector, this velocity vector, this is the speed at which he's coming in, right? And I could take that velocity vector and just think about flipping it, right? Because this is the vector, you know, if it was based up here, that's not really the vector, right? The vector's actual value is whatever these two components are. So if I think of the vectors being rooted at the origin, it actually looks like this, right? And so what I want to do is preserve this amount, right? So this outgoing vector here is going to have this amount right here, this x amount. It's going to have the same as the incoming. The outgoing velocity is going to have the same as the incoming, right? But its y component is going to actually just be the negative, right? You can kind of see that whatever we thought, however fast we were moving in that direction, we're going to flip it up to here, right? And again, we could, after we compute this vector, we could do various things to talk about like treating it as if some energy was absorbed in the impact. We could lessen the amount that it bounces this way. We could just lessen its speed in general if we want to go in the same direction, but lessen it. So we could think about various things to do here. And that is how we would do that bounce, right? But there's something interesting that I've baked in here. And this is the part where it starts to get, because, I mean, if you were to look at this, you'd say, oh, well, based on that description, Casey, it's pretty easy to understand what's going on. If this is the incoming velocity, so this is the old velocity, and I want to compute that new velocity, right? What would I do? Well, I just told you what to do, right? If v, right, is equal to vx, vy, right? It's got two components. It's got the x component of the velocity and the y component. I just said, well, the new one's going to have the same x, and it's just going to have a negative y. I pointed that out on the diagram. It's kind of obvious, right? There's not much to do. So why are we talking about this? And in fact, it doesn't even look like a vector operation. It just looks like we're operating on the scalars again. You know, and at this point, you're just like, I'm going to go watch John play Nuclear Throne on the other channel because, frankly, you're not teaching me about vectors at all. You're teaching me about scalars, and I already know about scalars. Fair enough. But there is a rub here. What I drew was the convenient diagram, where the axis along which we were doing this reflection was aligned with one of the primary axes, right? X happens to be the wall. And that is why it is y that can simply be negated. What were to happen if we had the same situation, right? Even still at the origin, let's say. But now I have a slightly inclined wall, right? And so I'm actually talking about a wall with this normal to it, right? This is the sort of the surface pointing out of the surface of the wall, right? Whereas here, the y-axis was pointing out of the surface of the wall. And now I've got this incoming thing, right? Well, now if I were to take that incoming thing and put it here, right? And look at what I want to have happen in terms of that reflection about the wall, because this is the wall, right? This is no longer the wall, this is the wall. Well, what am I going to do? That's not the y component anymore, right? These things have drastically different y components. There's the y component of that one, there's the y component of this one. Ain't no negative gonna fix that problem, right? You are not the man now, dog, if you think that you're gonna do this, right, to solve this problem. And so this presents us with our first sort of point where we have to start thinking about vectors in terms of the actual structure of them. In terms of the actual fact that they are vectors and not just scalars, because now we have to start thinking about how do we work with vectors in ways that do not involve falling back to the scalars when we need to do something on just one part of them, in just one piece of them, right? And so the answer is simply that we need to get familiar with, remember, I don't know if you guys were with me the whole time, then you remember me talking about something called the Hadamard product, right? And I don't remember is it 2Ds? I don't even remember. Is it that way or is it that way? I don't actually know. But I talked about the Hadamard product and I said, well, that's what happens, if I have two vectors and I want to multiply them together. I don't really want to write cross, I'm going to write that. If I have two vectors and I want to do some kind of operation between them that's multiplication, well, one way to do it, right, is to multiply the components together like so, right? A times C, and that goes in the x component, right? And B times D goes in the y component. That's called the Hadamard product, and that results in another vector. Well, that's really, like I said, not that useful for a lot of the stuff that we want to do. So now it's time to get acquainted with something that is very useful for the things we want to do, and that is the inner product, or better known oftentimes in game development circles as the dot product, okay? That is what is going to allow us to solve these kinds of problems with relative ease. You'll notice I don't have almond milk today. I've got tea. I'm doing some Bengal Spice. That's basically what's happening right now. All right. So, excuse me. Let's take a look at the dot product. Try to remember these diagrams. I don't have room for everything. So let's take a look at the dot product. What I wanted to do, right, is I already showed you how to solve the problem if everything were axis aligned. And so what I really want to do is I want to kind of have the ability to make my own axis systems, right? Like if I could have just created a new axis system that happened to be aligned with the wall, then I could have used the same solution that I used before, right? But I don't know how to do that. And so what we're going to look at now is we're going to look at how to use the inner product to do those sorts of things. So what is the inner product? Okay, so if I have two vectors, right? Here's one vector, and then I'm going to do this magical thing, the dot product. I'm going to do the dot product here. If I have AB and I'm going to do the dot product of AB with some other vector, CD, right? Then what this actually does is instead of producing another vector, meaning instead of producing something like the Hadamard product where it had two elements and it was another vector just like the two that came in, this is actually going to produce a single value as a result. It's going to contract these two vectors down into a scalar. And the way that it is defined, right, is it is defined to be the members multiplied by each other and added, right? So it's A times C plus B times D, right? It is A times C, B times D. Now, this jumps ahead a little bit for me to explain really how this is working exactly, because we haven't quite gotten into matrix math yet. But one thing that is interesting to note, and I'll kind of show you how this works, is the way matrices are multiplied is actually very easy, and I alluded to it on an earlier stream, in fact. But if we were to think about these as matrices, and we were to think about this the first part of the dot product here, this fellow right here, as being turned from a column into a row. So if we were to think about it being aligned this way, right? And then we take this guy and we leave him as his columnar form. And we construct the multiplication of these two in matrix notation. Well, matrix multiplication is actually very simple. For each element that you want to compute in the result, it's basically just as easy as drawing a line to find out where in each vector you hit for the element. Now, of course, there's only one element in this result here. If there was two matrices here, we'd have more of them. But then you just work your way down, starting from the outside first, right? A and C. You multiply them together, and then you add. You go to the next one down, D and B, right? There we go. And that is the dot product, right? Now, this works for vectors of any size. It doesn't matter how long they are, right? It doesn't matter at all. You still would know exactly how to produce them because as many as I have here, D, E, F, right? G, H, I, J, K, L. I just take the first ones, I multiply those together, GA. I take the second ones, right? BH. And I just multiply and add all the way till I get to the end, F and L, right? And that is how you can produce the product, right? Very easy. And so oftentimes, there's the operation of changing something from a row orientation to a column orientation like that is called a transpose. And so oftentimes you will actually see the dot product, and it's called the inner product as well, like I said, because of this exact look, how it looks like that. You're getting sort of the inner portion here, right? It's hard to say without the matrix because there's a thing called an outer product as well. If I were to flip these the other way, it would produce more values. In fact, let me just show you because it's kind of interesting. If I were to flip these the other way, C, D, A, B, right? I can produce the outer product. And again, I follow the same rules. Do that intersection, right? C times A. And that's it. There's nothing more to do in either that row or the column, right? So that's one entry in my resulting 2x2 matrix. Do it again here, D times A, right? There's another one, C times B, D times B, right? You can learn matrix math in no time because basically just learning that is all you really need to know and you can compute any matrix product that you want. But again, until we actually learn what any of these things do, not particularly useful. But I just want to show you that. This is an outer product, that's an inner product. And you can kind of see why it's called that because these two things like kind of form the smaller space there and the larger space here. But anyway, that's neither here nor there. All right, so the inner product, dot product, are oftentimes called the scalar product as well because it produces a single value, no matter how big the vectors are, is something that is of great utility. And it may not seem like a very useful thing right now because you're looking at that going, why would I ever care about that at all? But the truth is it's actually quite useful. And the reason that it's quite useful is because this value, despite its innocuous look, actually computes to something very handy based on what these vectors actually are. So let's take a look at what that actually is. And I won't probably go through the trouble of proving it all because math proofs are only interesting to some people sometimes. But point being, I'll show you the sort of the intuitive stuff and how to think about it. And if you want to know the proofs, I can actually, maybe we can talk about them on the forums or something like that. Anyway, so the dot product. If I have two vectors, so I'm going to go ahead and say that my vectors are now A equals AX, AY, right? And B equals BX and BY, right? These are my two vectors. And somewhere in space, right, I'm going to think about these guys. Here's my coordinate system, and I've got two vectors, okay? Like so. Now, when you compute the dot product, again, often written as this because of that transpose. The T means the transpose. Remember, I'm turning one on its side and then multiplying to get that thing. Oftentimes written like this, can also be written just as a dot and so on. There's lots of different ways to notate it. I tend to use that one, A transpose B, because that's just the same in matrix notation. So that's the dot product there, right? So that, which again is just going to be AX, BX plus AY, BY, that's the entirety of it, right? That's all it is. That quantity actually equals something rather useful. It turns out that it's equal to however long, and this is one way that length is often written, so I'm just going to write it that way for now, however long A is, right? And so I'm going to call this A, and this B over here. However long A is, scalar-wise, right? Times however long B is, scalar-wise, right? So that length here. So this guy is that length, and this guy is that length there, right? Times the cosine of the angle between them. So these two guys here, they've got this angle here, you're right? Let's call that theta. The angle between the two vectors, whatever its cosine is, times the length of B times the length of A, that equals this quantity. Because remember, this is a scalar, because this is a scalar length. That's how long A is, this is how long B is, and this is how long, and this is the cosine of the angle between them, right? Well, again, if you want to prove this, you use the law of cosines. If you know geometry, I'm not going to do it right now, but basically you can prove this using the law of cosines. If you're interested in that, you can go check it out. But anyway, this quantity constructs that actual identity, right? It actually, this scalar value equals this scalar value. And with just that one relation, we can do some incredibly powerful stuff, actually. So what stuff can we do? Well, for starters, what if we wanted to know the length of a vector? Like, I want to know how long A is, right? Well, there's two ways we could think about doing that, right? One is that I told you about the Pythagorean theorem the other day, right? So we could take, here's AX, here's AY. We want to know this length here. We could do AX squared plus AY squared equals whatever the length of A is squared, right? And so that is how we would compute that length. We would root this. So we would go, okay, root AX squared plus AY squared equals length of A, right? That's what we would do. And that is one way to compute the length of A in terms of thinking about how it's done, right? Another way we could think about how it's done is just by using this equation. We have something in it with the length of A, right? So what if we were just to take, instead of doing A transpose A, and instead of taking A transpose B and taking the dot product with B, what if we just take the dot product of A with itself, right? Well, if I take A transpose A, just following this equation, I would get the length of A times the length of A again, times the cosine of the angle between it and itself. Now, we know that the angle between it and itself is 0, right? So what's the cosine of 0? Well, for those of you who don't remember your sines and cosines, all right, you know who you are out there. I'm going to draw the circle. You could always draw the circle if you get scared, right? You could always draw the circle. This is the starting point on the circle, right? We wind up to here, right? That's 90 degrees. We wind to here, that's 180. We wind to here, right? That's 270. Wind to here, and that's 360 again, right? This is 0. Similarly, if you're doing this in radians, if you guys remember your radians, it's 2 pi out here, right? So this is going to be pi over here, and this is pi over 2, right? And this is 3 pi over 2. Remember the circle. As we work around the circle, right, the cosine is the x-coordinate of the point on the circle, and the sine is the y-coordinate of the circle. So if I was at 0, which is right here, right? Well, there ain't no y-coordinate. There's just the x-coordinate, and the x-coordinate is all the way out, right? So the cosine of 0 equals 1, right? Cosine of 90 equals 0. Cosine of 180, negative 1, right? Comes back around, and so on. Hopefully you guys are all familiar with that. If you're not, get used to your unit circle. Unit circle is the man now, dog. Is good. Okay? Unit circle, good. All right. So if I do this, and I know that this is 1, because the angle between A and A is always 0, right? It's right on top of itself. I know that falls out, and I just get length of A times length of A, which means ATA equals A squared, right? So the square root of the dot product of A with itself is the length of A. Not surprising, because guess what? This is the equation for the dot product, right? What would happen if these were A's? It'd be AX squared plus AY squared. Exactly what was inside my Pythagorean theorem. The Pythagorean theorem and the dot product are very intimately related, right? And you can see that. Okay. So, what else can I do with this? Surely I did not spend all that time teaching you how to do something that you already knew how to do and that we already did yesterday, and that's correct. I didn't. There's a lot more stuff in here that we can use. All right. What is it? Ooh. Whoops, didn't mean to quite get that. Overzealous. All right, there we go. All right, so what is it that we can do with that, right? What is it that we can do with A transpose A equals length of A, length of B, cosine theta? Well, the cosine theta is the part that really comes in particularly handy, right? The reason that that comes in particularly handy is because when we start to think about the cosine of the angle between those two vectors, right? If we start to think about what that actually means. Well, what if we could take one of these guys out of the equation, essentially? What if we could just say, a priori, let's take B, and let's say B is a unit vector, right? A unit vector is a vector with length 1. Right? So if I said the length of B was 1, it's 1 unit long, then it would drop out of here, right? And if B is length 1, then we get A transpose B equals A cosine theta, right? That's what we're actually going to get. So what does that actually do for us? Why would I care about that? Well, the reason I would care about that is because imagine that now we have our wall again, right? That wall we were talking about. Suppose we had, right, a unit vector that was pointing the direction away from the wall, right? Just suppose that's something we had. Well, now, if I have some other vector, right? I've got this vector here that's, this guy's doing his incoming bounce, right? And so this is the vector. That's that incoming velocity. This is that incoming velocity. So here's my vector, B, right, in this case. And I guess in this case, I want to say that this is A for our equation, right? So that incoming velocity is A. Well, if you take a look at what actually happens to these two vectors, I know that the length of B is out of it. So the result is going to be however long A is, which is this length right here, right? But multiplied by the cosine of the angle between the two vectors, right? And that cosine, again, is going to be this right here, right? And to see this a little bit better, maybe it's kind of hard on the diagram. Let me do it with a more, perhaps a slightly more acute way. Let me bring it out here, right? So that we don't have to have it sort of be bent back. Let's suppose that they were more like this, so they're a little easier to see, right? So I know my result is going to have the length of A in it, but I also now the cosine of that's between these is now going to multiply it out. And what does the cosine of a triangle do for us, right? What does the cosine of a right triangle do for us? Now you should remember this again from your grade school trig, right? What does the cosine of a right triangle give us, right? Well, it gives us this. It gives us this edge right here. If this is the hypotenuse, right, then this is cosine theta h, and this is sine theta h, right? That's exactly what that gives us. It gives us the length of that side, and the sine gives us the length of the other side, right? Times the hypotenuse, however long it was. Again, this is stuff you should hopefully all remember from your grade school trig. Well, what did that construct up here? If I was to build that right triangle, right, that's built off of this angle, I'm getting this. I'm getting this amount right here, right? That's what I'd be getting. Because I know that I've taken the length of A into account, it's right here, and I know I've taken that cosine ratio into account right here, so this is just like here. Just like h cosine theta gives me the length of this side in that standard right triangle that you're used to, length of A cosine theta gives me however long this guy is projected effectively onto this vector. So A transpose B is actually extraordinarily powerful because what it lets me do is it lets me take any unit vector that I want, anyone, and then for any other vector, no matter how long it is or what its shape is or what its direction is, and project it down to see where it would land on that vector, right? Now you can imagine this getting even more powerful. What if I had another orthogonal vector, right, that was perpendicular to B, also unit length, let's say this was C, so C is also unit length. If I took the dot product with that, I would now know both coordinates of this A in a new fictional space that I've constructed, right? Instead of the x and y axis being how things are measured, by taking both dot products, I would essentially create new coordinates for A, new coordinates in a coordinate system that I set up. So essentially this A transpose B allows me to measure any vector that I want on any axis system that I want, just by setting up two unit vectors that are orthogonal to each other, that are perpendicular, right? So imagine I want to do this. What are the coordinates of A in this new magical reference frame, this BC magical reference frame that I've constructed, right? Well, I just said what they were. They're A transpose B for the x coordinate. If this is my new x-axis, I don't know, maybe it's not. Maybe that's, I suppose this should be the x-axis because it's right-hand rule, right, going that way. So this is actually not quite right. Let's say that it's A transpose C, right, is my x-coordinate, and A transpose B is my y-coordinate. That's the new vector. And that tells me the coordinates of A in this space. Make sense, right? Okay. So hopefully you're clear on that. And again, you know, I worked through all of it to show you how that actually happens, giving you the right triangle and so on. But what you really, again, you want to internalize that and you want to spend as much time as necessary to get familiar with these guys. But the important takeaway conceptually, right, is that measuring process. Okay, it's that measuring process. It's saying that a vector, right, dot a unit axis equals the coordinate of that vector along that axis. Make sense? Now this works even for the axes we already have. So if we were to actually take the x-axis and the y-axis and do this, we'd get the right answers. Why? Because what is the x-axis, right? What is the y-axis? Well, if we represented them as vectors, we'd get 0, 1 for the y-axis, right? There's no x component and it's going 1 in y. And for the x, we'd get 1, 0. Well, what happens if I dot product those with some vector in the space, right? If I have ax here and ay, what happens if I dot that with one of these? Well, you should be able to do that right away. You know it's ax times 1, so that's ax, and ay plus ay times 0, which is 0. So it's just ax, which is the x-coordinate of the vector in that space. Same is true if you did it for y, right? So this is like the universal measuring operator. It has a lot of other uses besides that, and we'll see them later on. But that's the one that we're going to talk about right now, because with that in mind, with that power, the old thing that looked so complicated, where how are we going to deal with this arbitrary wall, becomes trivial, right? Totally trivial now. So let's go back to our diagram that we had before and see if with the dot product we can now solve the problem that was so sort of weird before and difficult. Oops, get that in there, right? So what I'm going to say is for any wall, in order to do a reflection off of it, all I need to know is I need to know a unit vector that points out of the wall, right? Also called the normal of the surface oftentimes, right? So there's my reflection. And I'm just going to call that, I'll just call that W for now, right? We'll call that our wall vector. Maybe I'll call it our reflection vector. Do you want to call it R? I don't know, it kind of sounds like rotation. We'll call it R. And what we have to say is R, the length of R is going to be 1. R is a unit vector, okay? So now I take anything that comes in that I want to reflect. Any vector, right? So this is my v, this is my velocity, right? And again, I'm drawing it coming in here because that's the physical version of the diagram, but really any vector is, you know, if we think about it, it's at the origin, right? So this is actually my v. And now what I want to do is I want to reflect that around here. I want to reflect that around here. So what do I need to do to reflect it? Well, I said before that what I need to do to reflect it is negate its y component when it was lined up with the y-axis, right? So all we need to do now is figure out what part of it we actually would need to negate in this new axis system, right? If this were the y-coordinate. So how do we do that? Well, I just said I can measure any vector along another unit vector, which is what I have. So if I take v transpose r, right? If I take that, that will project me onto that vector, right? So v transpose r gives me this vector, well, actually, it gives me a scalar, right? It gives me a scalar, which is how long this actually is along that vector, right? So now the question is, that's the quantity I need to negate, right? I need to make sure my new v, my v prime, right, my new velocity, basically is the negative of that. It's going upwards. But this is a scalar quantity. It's just a number. It's the measure along here. How do I actually, I need a whole vector for reflection. I need to construct this whole vector. So what do I do? Well, it's pretty easy, right? If I were to start, here we go. If I were to start by saying, well, all right, I have my v, right? I now need to change it so that I'm going to get it so that it reflects through here. I just need to add something to it, right? That's going to move it up so that it will have that reflection. And I know exactly what that quantity is. My v transpose r is the length along r that this was, right? And that's going to be negative, obviously, because we know it's going into the wall, so that's going to be negative. So if I multiply that scalar times r, times the actual wall reflection direction, right? That gives me a vector. That gives me essentially this vector right here, right? That's actually the vector now, not just the length. So all I have to do to reflect this across it is just subtract 2 of those, right? Just to move it up to here first and then up to here second. If I just subtract 2 of those, I will flip the vector around and have it go out in the other direction, right? So again, just constructing it very much like it, just doing what I want to do with it. So if I take the old v and I subtract 2 times the quantity over here, right, where I've got my v transpose r times r, right? That will start at my v. That will figure out how long it is along the reflection vector. It'll move me back to the even line. This will move me back to the wall, this first one, right? And then by doing 2, I then move myself basically to the mirror position. And this was a bad drawing of where that would be. It would actually be like over here or something, right? So my new v prime is just that. That's the entirety. That's all I have to do. I just have to take my incoming velocity. I just have to subtract twice whatever that measure was along the reflection vector, and then move it in that direction along the reflection vector, right? Makes sense? And that is, of course, if I've done the math right. Like I said, I'm horrible at math, so anytime we compute something like that, we need to then go test to see if I'm right, because a lot of times I'll just make a straight-up mistake. Okay. You know what I just realized? I just realized my Linux has hung completely, which is unfortunate, to say the very least. All right. Well, that's all right. We'll go ahead and get that rebooting. It has not been a good week for Linux, ladies and gentlemen. It has not been a good week for Linux. My Linux crashes all the time now. It's very unfortunate. Anyway, so this is what we need to implement. And all we really need to do is anytime we want to bounce something, we can just go ahead and say, let's go ahead and define some unit vector in the direction we want to bounce, and we can bounce. And now we are not restricted to just bouncing off of things that are going to be, aligned with an axis system, which would have gotten us a certain, a certain degree of the way, certainly, right? We totally could have bounced off just the tile map edges using that. But as soon as we want to do something fancier, it would not have worked, right? Because if we want to have some kind of a slanted wall in there or anything like that, we'd be out of luck. All right, I'm going to go ahead and take 1 second here to go ahead and start the hex chat back up. So I will actually be able to see questions at the end. So sorry about that. Again, not the best situation for Linux. Let's see. Is it so hard, people? Is it so hard? It is apparently so hard. Okay, hopefully that'll stay up long enough for me to answer the questions. Okay, so let's go ahead and do that. Let's go ahead and just implement this. So I now want to do a thing where I compute that bounce. And in order to do that, I know that I need a dot product. So we'll open up our math routines and add one. So in line, again, it returns a scalar value, inner product. It takes 2 things, and I might just call this inner because it use it so often, it's pretty obvious what it actually is. And so the result here, again, very straightforward. It's just ax times bx plus ay times by. Okay, there we go. Return that there. And so that's our dot product, inner product, scalar product, whatever you want to call it. And that is what we're going to be computing to do our reflection code. And so if we want to reflect here, basically this is in the case of the tile point not being empty. I guess what we could do is say, all right, then if the tile point is not going to be empty, then we basically have to figure out what direction the wall was actually in, which we haven't actually done yet, but let's pretend that we do have that. So we basically have our r, again, this is going to be some value here, which again is that r from this equation. And what we need to do is take our velocity, which again we have, it's the game state d player p, and what we need to do is reflect it about there. So what we need to do is say, okay, we've got the d player p, and the new d player p for this frame, or I guess, have we actually retired the point yet for this frame? We did the test, so I guess it'll just be for next frame, for this account. So we take that d player p. We're going to have to work on this player motion code a bunch, to say the least. But anyway, we're going to take that old d player p. We're going to subtract 2 times the inner product of whatever it actually is, and our wall vector, right? And then we're going to multiply that by the wall vector itself, right? So there we go. That's the actual equation that we need to use. And oops, those were lowercase. They should not have been. I wonder if I should make those lowercase. It's a good question. It lines up better with the shader code if you make them lowercase, because shaders have .x, .y, that sort of thing, if that makes sense. All right, so what we need to now know is what actually is that. So let's hard code it first to make sure that we actually have our stuff working at all. So if we actually wanted to bounce off that bottom wall, that bottom wall is going to be obviously just the y-axis. So this should do the initial thing that we just sort of said was what we would do if we didn't actually have the dot product or any of that stuff. So let's see. There we go. Of course, that's pretty funny. Yeah. So there we go. No problems there. Seems to work pretty good. Of course, I'm accelerating against it, so I kind of there we go. Yeah, so that's pretty straightforward. Nothing much to see there. Now, of course, the problem would be if we actually do that, we would have the wrong, we would have the entirely wrong behavior because we're not actually computing the wall correctly. So what we do need to do is figure out some way to actually figure out what the direction of the wall is that we ran into. And I don't think we really know very much about how to do that at the moment. I guess we would have to sort of say, well, when we check these points, right, the new player P, the player left, and the player right, we need to figure out which ones of them are not actually allowed, because we don't really have much in the way of collision code at the moment. We'd have to figure out which ones of those were interpenetrating, and for whichever ones were interpenetrating, we would then have to figure out which direction the step was between the current position and the new position, like which direction we stepped in the tile map would tell us where the wall is. And this is one reason why, you know, like I said, later on, I don't think we're going to be doing any collision detection on tile maps because it's just kind of annoying, and I don't think we probably want to have like a more interesting boundary around things. So yeah. So I wouldn't basically put much weight into this particular stuff, but the bounce code is correct, and so let's keep going with that. Anyway, so let's say that what we do here is we take a look at these guys. I guess we could just say whichever one of these, yeah, this is kind of ugly, but let's just do it because we might as well, we're here. So we've got a bool 32 that's going to say, you know, I guess, well, you know what, I don't even need one of those. Well, I do, yeah, I do. Okay, so we'll just say collided. And again, this is really bad. This is not at all what I would advise doing, but I just want to, we're working on the wall code right now, so I don't really want to spend any time thinking about it. I just want to do something where we can get our wall out and go. And since we know we're not going to be doing collision detection this way eventually, it's not particularly interesting to me to think about it much more. So basically, if the tile map is not entered there, I'm going to say collided equals true, right? Like this. And then I'm just essentially going to do that same thing here. So player right, and player left. So I'm just going to take a look at those collideds, and if I did collide, then what I'm going to do here is say that there's a tile map position, call P or whatever, and that's going to equal in the case of collision whatever we actually found was the collision and trigger, right? Whoever actually collided. And this will let me know what actually caused us to not move, right? And so this now becomes collided. If we did not collide, right, then we can go ahead and do we can go ahead and do our stuff. And so that shouldn't change anything as it is, right? We should still be able to do whatever we were doing before. But now we can compare and figure out where our wall actually is, right? So if we want to see where the wall is now, we can essentially say, well, we know we collided whatever we actually found, and player left. So I'm just going to take a look at those collideds, and if I did collide, then what I'm going to do here is say that there's a tile map position, call P or whatever, and that's going to equal in the case of collision whatever we actually found was the collision and trigger, right? Whoever actually collided. And this will let me know what actually caused us to not move, right? And so this now becomes collided. If we did not collide, right, then we can go ahead and do we can go ahead and do our stuff. And so that shouldn't change anything as it is, right? We should still be able to do whatever we were doing before. But now we can compare and figure out where our wall actually is, right? So if we want to see where the wall is now, we can essentially say, well, we know we collided, right? And so in some sense, we could reverse the sense of these so that we can get rid of that knot there so we can actually see more cleanly. If we collided with something, we just need to figure out what our wall is. To figure out what our wall is, we then go, all right, we know col P is the thing that collided. So what we need to do is take whatever the player P is, right? Whatever the player P currently is, which is this guy. And we just need to see what direction he was trying to go in the tile map, right? So if you remember here, we have the tile map position. We have abs tile X, Y, and Z. So we just need to look and go, all right, if the abs tile X is less than the abs tile X here, then we know that this wall was a wall going in sort of in descending. The player was moving from like to the left, right? The player hit a wall to the left, and we could do the same stuff in all the directions. If it's greater than, and if it's that, so on. And since we can't really make anything collide diagonally at the moment, I guess we don't really need to worry about that case. But anyway, here we go. We can basically do, I think people were saying we could do this, right? Yes. So, given that we've got, what was the complaint? Oh yeah. So given that we've got that, we basically just need to define the wall for each of these motions. So in this case, I'm moving to the left. So that means the wall is like, it's normal pointing out to the right. In this case, I was moving to the right. So I have the wall pointing to the left. In this case, I am moving up. And so the wall is pointing down, right? Is that correct? Yes. Wait. No, it's less than, so it's moving down, so it'd be up, right, and then that. I believe that is all of them. Potentially understood col P is used. Well, if it collided, we know that, well, all right, fine, we'll just do this. There you go. And we know that these cases can actually happen, but the compilers are being a bit persnickety there. So in theory, that should give us bouncing off of all the walls. Yeah, there we go. Right. And so now we're just a bouncy little fellow who's pretty happy about his lot in life, very determined to go around bouncing along things. And the faster we go, the harder we bounce, which is exactly what we wanted in terms of our behavior. Now, like I said, if we wanted to, we could make him bounce a little softer off things by basically adding a coefficient in there. It's called a coefficient of restitution. The coefficient of restitution would basically be some number less than 1 that we would multiply our vector by to reduce how far out it went.